Alrighty, deja vu, me again. All right. This also I will attempt to go slow enough for you to comprehend. This topic, of course, is very detailed. We have a discussion group that I've set up, JEE Talk at Yahoo group. Go to our website and subscribe to it. You can ask as many questions after the meeting. Discussions are always ongoing, and we are in the midst of a special observing session where we're getting a really complete map of Europa's atmosphere right now. It's going spectacularly well. And I'm going to be presenting actually next Thursday to NASA's Division of Planetary Science. I'm going to be presenting to Fran Bagenal our results, and she is the principal investigator for the Juno space probe that's on its way to Jupiter right now. So they're interested, very interested in collaborating with us. I thought I'd go over some of the basics here because there seems to be a lot of misinformation on occasion circulating on the IOTA discussion group about what we're doing. It's always good to go over the basics anyway. It helps to keep you grounded as to where you're at and what you're doing and what your limitations are. There are limitations. Let's go to the next slide. And we see what is a JEE. Our Jovian Extinction event is a dimming that we capture photometrically with a, video or CCD. We've had both observations submitted now. And the way I describe it is the front moon or object that is being measured, we call that the target, and whatever passes behind it, line of sight, we call the probe. And so what happens is the light from the probe is affected by the debris from the target. Since the discovery in 2009, we've had, I think we've crossed our 100 data set submission already. I'm definitely going to check into that. Let's go to the next slide. And for you to graphically see what the JE looks like is here is an occultation of a mutual event in the center. And then out in the wings, you see a gradual dimming and brightening surrounding the occultation. That is extinction event that was captured through much longer wing data, and which is why this has been missed. Let's go to the next slide. Why it's been missed is the typical wing data in a Jovian mutual event is about 6 minutes long. We have to look over periods of an hour, sometimes two, in order to capture an entire extinction event. This drawing is sort of a schematic to give you an idea of what is the geometries that are involved. This particular case is EO's atmosphere, which is approximately 8 radii out, and dimming and varies actually, which is no surprise since it's very active moon. Let's go to the next slide. So this is the question for the group. Can video provide accurate photometry? The answer is yes, within its limitations. I've been collaborating for 3 years now with Arnie Hendon on this. He is the head of AAVSO. And when I sat down and talked with him the first time talking about this in 2010, he said, I'd expect video would probably get about 15 millimag standard deviation. And he was pretty much right. Using some of his and Brian Warner's suggestions, we routinely achieve about 10, 15 millimag standard deviations. Let's go to the next slide. So how we do that has been an evolving process, number of steps. So for NTSC video, we get about 30 frames a second. For PAL, we get 25 frames a second with 8-bit, approximately 8-bit data resolution coming out. We then bend 10 full seconds minimum of data into one single data point. This statistically eliminates scintillation noise statistically, and as well as camera thermal noise, and a number of things are really beat down to insignificant numbers, which allows us to reach the standard deviations we are. So mathematically what we see is if we have 256 range video and we're bending 300, that gives us about 16-bit, actually a little less, probably 14-bit statistical resolution, because you lose some in the camera because it's not typically 0 to 256 or 255. But at any rate, that's some of the numbers and statistics for those who are curious. Here's an example, next slide, of how well our achievements can be. This is 165 minutes straight of videoing Jupiter's moons. In this case, it's Europa is the target. And the Jupiter was only 18 degrees up when I started this recording. It was 52 degrees up at the end of the recording, and we had a standard deviation of 10 millimeg on that. Let's go to the next slide. So one of the things we did early on, and we continue to do to validate our work, is look at where the proposed sources of these dimmings came from, and to validate or invalidate the actual theories behind them. So one of the first things we did was look for reduction techniques possibly introducing these dimmings. Go to the next slide, and simply red X that shows that this was proven to not be the case. Let's go to the next slide, and we'll demonstrate how we eliminated reduction technique as introduction of the noise. Here is a raw intensity plot from two different data sets of the same event. In these pairs of peaks, the peak on the left is EO, the peak on the right is Europa, and you can see in the change in time as they get closer, peak on the right, which is Europa, our probing moon, dimmed relative to the other one. You can see that its peak gets smaller, and you can see it in both data sets independently. This being raw intensity profile has nothing to do with reduction. This is simply looking at the data from the CCD. Let's go to the next slide. We see through another, when we do separate photometry in that particular event, we see that EO, being the front moon, the target moon, did not change in brightness, while Europa, as it passed behind it, is the one that lost intensity. So that shows that the source of the dimming was Europa dimmed as it passed behind. Let's go to the next slide. And we see another way is to randomize the reduction method. So here is the same event reduced two different ways. If you look up in the legend, I'll define what these initials mean. So you see T-reading data, and you see that Europa was normalized to EO, and that's the red circles. I reduced mine a different way. I put a circle around EO and Europa, included them all in the same within the same measurement aperture, and then normalize their light to Ganymede. And you see the data overlays, and there's a really nice fit to it. So two different reduction techniques, methods, and normalizations give the same event. So therefore, it shows that it's not, dimmings are not tied to reduction, but something in the event. Let's go to the next slide. We see the next proposed source of the dimming is camera response. There were initially people, and including myself, who said, well, I wonder if the camera is causing this. There's only two ways this could be introduced, either randomly from two emerging light sources, or systematically, meaning that the dimming is tied to the geometry of two light sources, which then would mean it would be linked to field of view geometry. So if we go skip 2 slides, there we go. We see that so what we did is we took two different geometries. Terry Redding provided an excellent source of this for the September 23rd event in 2009. He put a 3 times Barlow in his 14-inch Meade, shot at a 9 meter focal length. This gave me such a high magnification that I was easily able to do individual photometry on the two moons involved, and showed once again in yet a different event that Europa dimmed relative to EO as it passed behind me. If we go to the next slide, simultaneously, while recording through his 14-inch, he recorded through his 80-millimeter finder scope. And so we have two vastly different field of views overlaid on each other, which gave exactly the same dimming results. Using two different field of views now unties the camera response as being the source. And the other, let's go to the next slide. The other thing that we get is we're getting consistent results. Here is a current table I have working of the various measurements we have of EO. You even see the variability in it. You see it goes from about 8 radii to over 10 for some period of time. So, you know, again, EO is an active place, so we would expect to see this. So let's go to the next slide. Let's remove merging light sources as the cause. It's yet another way to chase down the source of this. So the material that leaves EO is trapped in what's called a torus ring. So if you go to the next slide, you'll see an actual image of the torus ring taken from the Catalina Observatory. And I propose that out at the torus tips, where material is collimated very long, over about 100 EO radii, that as, let's go to the next slide. You see the schematic of what I'm proposing, that as EO gets behind these tips, you have an extended collimation of material that is the same material that is causing extinction around EO. Therefore, if it's the same material, it should cause extinction out here at the tips. So if you go to the next slide, you will see that this was validated by this nice 5-hour recording from John Talbot in New Zealand. We were able to get a fifth order polynomial fit to this that I now use on all torus reductions, and it fits every time. So what we got was about a 0.13 magnitude drop. Now this is back when Jupiter was the orbital plane was 0.4 degrees, almost edge on. It's not 0.4 degrees now, so we get the same profile, only a lot less because it's not edge on until next year. Let's go to the next slide. So all of these are just squiggly lines unless we can link them to something. If you go to the next slide, you see that the JPL offers us a web service called Horizons. And the Horizons data is the exact same data used to guide our spacecraft. It's probably the most accurate ephemeris you're going to find on our solar system. And so go to the next slide, and we see that we can take some of the published data. We see that Schneider, who I'll be presenting to next week actually, took early measurements and said that there is a sodium corona that goes out to at least 6 EO radii and falls off more steeply after that. So let's take that number and go to the next slide. Using JPL ephemeris, I'll take this event on September 1st, this light curve, and let's put it up against the JPL Horizons data. So we go to the next slide. And I called this our envelope of sanity. Taking the Horizons data, I simulated an atmosphere and said that when the moons are within certain defined separations between 6, the green dash line represents a 6 radii atmosphere, and I put an outer limit of 15 for the red dash line. If our data falls within this envelope of sanity, that definitely means that we can link it to geometries of the moon based on ephemeris from JPL. So we go to the next slide, and we see that our data falls perfectly in the envelope of sanity and fits very well. So we end up with this fit of 8 EO radii and experienced about a 0.18 if you were able to see in the center of this about 0.18 magnitude drop. So let's go to the next slide. Let's take Europa. Europa, according to Brown et al., said about 25 Europa radii. Let's go to the next slide. And so here is, we don't have many Europa events. We're starting to get more now. That's what we're in the special season in 2013. There's a lot of Europa events. But back in 2009, 2010, we got a few. Here is a fit from one showing 18 Europa radii and about 0.25 magnitude drop. And you would expect the drop to be deeper since, and by the way, the material around Europa is the same stuff from EO. First it's bound to EO, then it gets trapped in the torus ring, and then it wafts out into space and Europa sweeps it up. So Europa sweeps up the exact same material, so it is extinctive just like it is around EO. Let's go to the next slide. Taking JPL data, I can, ephemeris, I can also plot things differently. In this particular plot, if you look at the top, instead of it being photometry versus time, this is photometry versus radii out from the center. It allows us to see geometrically where events occur relative to the center of the target body. Let's go to the next slide. We'll skip that. That's our current working theory is that those two horns you saw in the last one are from possibly from material trapped in the walls of the flux tube, just like they're trapped in the torus ring. Okay, next slide. So let's, for instance, let's take this torus light curve from Talbot and let's put it, overlay it on top of ephemeris from JPL. Let's go to the next slide. And what it should do is, number one, it should look a lot like the torus ring, and it does. And as in more confirmation is we find that the max extinction occurred at the back of the tip, which is just like the schematic I showed you earlier predicted. So from this you can derive things like, all right, you have a column depth of 73 kilometers, extinction of 0.13 magnitude. We're working currently on getting calculations as to what type of density of material and size of the particles would cause that. It's one of the things coming up. Let's go to the next slide. Then there's the Hubble challenge. I get asked this all the time. Why can't I see extinction around the moons in front of a picture from Hubble? Well, the answer is you can. You just have to know how to look. It's not as obvious as one would think. Let's go to the next slide, and you'll see where I took this. That was a raw image provided to me by a professional astronomer who issued me the Hubble challenge, I should say. And I took the Hubble challenge, and what I did was I just simply drew an intensity line out and displayed what the intensity looked like. And indeed, you see the gradual brightening in the upper right of the outside of the body. We'll go to the next slide, and it's out 7.5 EO radii. And this is a crude measurement. This is by no means, Jupiter is not. The reason I avoid this is Jupiter, as you see, is a modeled object. It's very non-uniform in brightness. This is not something that it takes hours to extract a usable image. If you wanted to try it, do it through an image. I like to do it graphically like this. And very crudely, we see that that magnitude drop is about 0.12, which isn't far off. Again, being a crude measurement, still pretty close to what we're getting. So there is a dimming there. It's just not easy to see. And there's so the conclusions are we get about 10 millimag standard deviation if you are careful. Dimmings are independent of camera observing system and reduction technique. Our O-C comparisons to professional ephemeris show that we are consistent in our geometries and measurements. And raw images from Hubble telescope can show somewhat consistent results of JEE data. The rest of my presentation is simply for you to download. There's an appendix with additional light curves and all that. So I think go to the next slide if you don't mind. I got those conclusions. But anyway, here's our links to our websites. Yeah, so the other conclusions are, yeah, we're getting about 8 to 10 EO radii. It varies. Europa, our newer measurements are around 20, so it varies, which doesn't surprise me. About 18 to 20 Europa radii of extinctive material. And so far, we have very few Ganymede events, and we have no Callisto events, but nothing's been detected around Ganymede. Published results actually don't say that there's any form of atmosphere around Ganymede. So again, independent confirmation that we are or are not measuring. So here's our websites. This is our discussion group. I'll log off now and let someone ask questions.
Okay, thank you, Scotty. I see from Roger it says, Paul, I have a good friend who was raised in, is that Nashik? The capital of Carabadine, Balkar, near this path, just north. Very good presentation, Scotty, convincing too. Switched over. Steve says, what does the dimming look like spectrally? Let's see, Scotty, you want to respond over the microphone? I'll release the microphone to you. Two messages mixed there, Terry. Extremely good talk, Scotty.
All right, assuming you can hear now, I'll respond to Steve's question there. And it's a question we all have, and it's a question that we're actually all working on. Last year, we actually got AAVSO to join in on our effort. And we've had about 3 or 4 people who have submitted color information. It's been a bit of a slowdown in being able to reduce that information because, number one, they took data with a single image periodically, which doesn't have the same cadence as video. So we're still working on how to tie that into our measurements. Number two, the answer to that is this coming up, 2014 is when Jupiter's orbital plane goes edge on again, and in September the mutual event season starts again. At that point we will have very consistent deep occultations, and we are all right now gathering filter. I just got a filter wheel last week donated to me from the University of Colorado to do multicolor video, and there are a number of members. I think Ernie Iverson may be one of them that is has color filters, and we're going to begin to try and take it in multicolors to then try and identify the source, what color spectrum is the dimming coming from. And the University of Colorado, as I was telling you, the Juno Space Probe group is interested, and the collaborator, Pro-Am collaborator, Wayne Green, is getting a spectrometer configured on their observatory right now to try to do spectrometry of these events as the events start to pick up probably towards next year. I mean, we're in a season right now through the end of December where we have an event every 3 days. But they're dimmer events, and they also don't have their 24-inch online in Colorado yet. So the answer is we are working on spectral data. We do not have it yet. I offered a spectrum challenge 2 years ago. John Menke's one who's tried at it, Manick rather, or Menke, and he's tried it. He's got a new spectrometer. He's going to try it some more. I offer anybody out there to try and do it in multicolor with video. The problem is our initial multicolor was in CCD, and it's not so easy to tie it to very continuous video. Hope that answered that. Anybody? Oh, Brino has a question. Sorry. On what is base slope and shape of the extinction model curves? Okay, so I think I understand your question, Brino. Brino's in Rio de Janeiro in Brazil. He's one of our JEE observers who works with closely also with the Brazilian National Observatory, who is hopefully going to join in on some of the upcoming events. And so the slope in the light curves are fitted by taking JPL ephemeris and saying, introducing into it an atmospheric size. Say, for instance, for EO, I'll start with 8 EO radii and saying that there is a spherical, evenly distributed material around EO. And I instruct the ephemeris to display for me what slope of dimming would occur if I had that particular model of a evenly distributed atmosphere with linear extinction rate from the center working out towards the edge. And so what I do is I get the JPL ephemeris to fit the slope. And then when I get that fit, I have the numbers, which are X number of radii with X number of dip in extinction, magnitude of extinction. And so then that's the fit that I put into my table. And I also have another method that I haven't displayed here. It's what we're taking to an Icarus paper coming up next year that we're working on, where I can take the light curves and I can invert them to be a graphical representation. And I'm taking all of those chords, just like we do in asteroid occultations, where you can take all the individual chords and display them together, and then you actually can see the entire atmosphere surrounding each one of these moons by putting all those chords together. That's what I'm going to be presenting next week. Didn't have enough time to present that here. So I hope, Brino, that answered yours and everybody's question, that the slopes are fitted by simulating the atmosphere with JPL ephemeris. Anybody want to type in any other questions? Okay. Ted had a question. I must have missed it. All right. Anyone use stellar probes? Yeah, at a much higher resolution. Yeah. So it's not often that the Jupiter system passes through a bright star field. However, using Dave Harold's occult, I have posted in my predictions online. You can download my predictions, which currently go to the end of 2014. Stellar occultations, you might call it, stellar extinction events, where somewhat bright stars will pass behind the Jupiter system. And so I haven't looked at the Taurus tip extinction events are harder to predict for any other object other than EO. But keep in mind, EO passes through there every day, once a day. It has an orbit of 1.8 days. So every 0.9 days, it's either going through the eastern tip or the western tip. So there's plenty of opportunities daily with EO. And I post those predictions online too, of every single transit of EO through the Taurus tip. Hope that answers your question.